Hi, my name is Christopher Duracco. Today I will be presenting the paper Topology, Perturbation for Detecting Malicious Data Injection for my Georgia Tech class CS6263. This paper was presented at the 2012 45th Hawaii International Conference on System Sciences by various authors from the University of Illinois at Urbana-Champaign. Now, the goal of this research is to detect malicious data injection in power systems, and as you can see, a lot of this infrastructure is very important. So it's really important to keep these systems up and running, especially a power system. So therefore, the solution presented is to use a probing approach in which the operator of the system applies known perturbations or deviations on the system caused by outside influences on the system. You may think that this kind of is a simple solution, right? You have a measurement. If the measurement is incorrect, you can detect that, oh, something is wrong with the system. However, it's a little more complicated than that. I'm going to get into it further in this presentation, but attackers are smart and they might know the topology of the system, and therefore a simple adjustment in measuring will be easily detected by the adversary, and they can figure out how to essentially fool you and fake the sensor measurements. So in this brief overview, they present a solution where the operator of a control system or power system is able to apply a perturbation on the power system and is able to take the observed measurements and the previously calculated measurements to see any abnormal behavior. The abnormal behavior can be anywhere from a misconfigured sensor or a malicious data injection to spoof a value, as I mentioned before. So to further describe the problem at hand is that malicious data can affect critical infrastructure. For example, SCADA, the supervisory control and data acquisition system, collects sensor measurements to estimate the state of a system and uses actuators to control the system. Whether it be a power grid, a water filtration system, or another industrial control system, these systems are an attractive target for adversaries because of the reliance these systems have on everyday life. So a adversary may be able to insert fake control commands into the system, therefore controlling the system, telling the power system to do something it's not supposed to do. The adversary can also delay measurements. This could have a major effect on everyday life, as in if these systems don't get the proper measurements, they can't provide the correct commands to the rest of the system, and therefore the system won't function properly. And the same thing if an attacker inserts a incorrect measurement. The control system will take that incorrect measurement and do something that essentially the operator does not want the system to do. Unfortunately, solutions developed today are not robust enough to prevent malicious data injection attacks. For example, state estimation in power grids are focused on faulty sensors and not malicious data. An attacker with knowledge of the power system topology can inject false data into the state estimators that use linearized power flow models. And because the attacker knows the topology, he or she can initiate this attack without being detected. Furthermore, standardized values are predictable and again are easily exploited by an attacker with knowledge of the power system. Hard-coded values like this will not help if the adversary tries to spoof a measurement, because the spoof measurements may look like the expected measurements from the operator's point of view, indicating that nothing is wrong with the system even though an attacker has infiltrated it. So therefore, we need some sort of probing method that an adversary cannot predict, and this paper has the proper solution for it. So to further explain the solution is to apply known perturbations into the system, also known as applied stresses on the system from an outside influence. Operators can see the change it has on the system and observe any unexpected behavior. So essentially, the operator is injecting these known injections into the system, and we're seeing how it reacts. And by that, we can see if something is wrong with the system. These perturbations will be changed or not changed. And based on that, we can see if something is going wrong with the system. Because an attacker may be smart enough to adjust the typical sensor measurements and other actuators in the system, but he may not know the known perturbation that the operator has just injected into the system. So a perturbation isn't just simply sending more power and having standard sensors pick up these values. This would be more predictable and vulnerable to attackers. The values the operators are looking at are the changes in the current or in the line impedance. The adversary may not know what the expected line impedance should be after an injected perturbation, making it harder to manipulate the system without discovery. And furthermore, to produce unpredictability, the probing signal that we're using to inject the perturbations is hidden and only known by a few operators in the system, making it very hard for the attacker to predict these values. The solution presented is applying known perturbations into the system. Operators can see the changes it has on the system and observe any expected behavior. So essentially, the operators are previously sending in these perturbations, seeing the results, and then running the perturbation analysis on the live system. And they can take those observed results and the expected results. And if the values don't match up within a certain range, the operators of the power system may be able to determine that the system is either faulty or that a data injection attack occurred. An example of a perturbation isn't just simply sending more power and having standard sensors pick up these values. This would essentially be predictable and vulnerable to attackers who know the power system topology. The values the operators are looking for in these probes are changes in current and line impedance. The adversary may not know what the expected line impedance would be after a injected perturbation analysis occurred. This makes it extremely difficult for the attacker to manipulate the system without discovery, because most likely the attacker won't know what the perturbation values should be. Furthermore, operators of power systems can set up continuous probes sending in different perturbations every hour, making it extremely difficult for the attacker to predict what the expected value should be. There are a few ways to probe the system, such as using voltages to change reactive power output in certain parts of the system, but in this case, the researchers determined DFACs, which are distributed flexible AC transmission systems. These DFACs sit on AC transmission lines and are capable of performing active impedance injections, making it a good candidate to probe the system. By changing the DFAC settings, we can measure the changes in reactive line impedance, also known as the resistance in an AC circuit. The operator is able to calculate the changes in line flow that will be affected by the change in line impedance with the equations presented on this slide, where X provides the predicted set of measurement values, K is a vector of impedance settings for defect-equipped lines, and delta X is the perturbation applied to the system. After calculating the results of equation 1, we can then use delta X and multiply it with the variable A, the expected change in response to the change in impedance. Then by adding M naught, which is the measured line flows prior to perturbations, we can therefore calculate a predicted value and subtract it from the observed value. Any values outside of an acceptable range should be flagged and looked at. This type of perturbation is very hard to predict for an adversary. Calculating the line impedance can be done with a simple AC circuit, but calculating the line impedance passed on an unknown defect setting would be very difficult, making it hard for the attacker to inject false data and affect the system to match the perpetrated values. Furthermore, this defense is only effective if the perturbations are secret. And even though the perturbations are only known to a few operators, there is a chance that the adversary may know the perturbations that are used on the system. Therefore, a key space is defined with the keys that are a vector of impedance values on the lines with defects. Similar to a private key in cryptography, these keys are determined on constraints and limits, and this private key is secret. It should not be known to the attacker. Now, when designing the keys, the designers may want the acceptable power loss on the perturbation to be within, let's say, 1 or 2% of power loss. Therefore, the keys must be small enough so it doesn't affect the system in a negative way, but they must be large enough to produce unpredictability. Now, in this experiment presented by the researchers, MATLAB was used to analyze the key space size and properties. MATLAB can be used to create a linear solution analyzer. The tool analyzes key spaces to determine if a sensitivity matrix produces a sufficiently accurate model for each key. You can think of the sensitivity matrix as the change to impedance to changes in measured values after initiating perturbation. So we're essentially comparing, a sensitivity matrix is comparing your previous values and the values after a perturbation. Furthermore, the analyzer can compare the linear solution and the full AC power solution. And if the difference between the solutions is within acceptable error range, it declares the key as valid and should be used in the perturbation of the power system. A lot of this research focuses on determining the key space because it's extremely important that your probing doesn't negatively impact the power system. There is no point to adding security to the system if the baseline of the purpose is no longer functional. Now, using MATLAB, the researchers were able to analyze 6 different bus systems used to connect major components in the power system. The legend on the top left here shows the different types of bus systems they used. For example, they analyzed a 7-bus case, a 38-bus utility case, and a RTS system. The RTS system was used in further testing in the experiment, and we're going to discuss a little of that later. But for each of these bus systems, the researchers calculated the raw key spaces using about a 20% maximum change in line impedance with an acceptable threshold of a 1% power loss. So essentially, the goal is to produce a key that's large, but only produces a 1% power loss. Now, each operator and designer can have their own constraints. when deciding on the size of the key. Other constraints may be a linearity constraint. In other words, it is the expected changes in linear analysis, or maybe an observable constraint, which means that the probe must actually produce results that are observable and not hard to see. This result here shows the power loss heat map for an RTS system with 3 DFACT equipped lines. The researchers further analyzed the effect of this key space and the power loss on an RTS system. As shown in figure 2, only 3 lines with DFACTs equipped lines is enough to obtain a large key space within a 1% of the minimum power loss. In this paper, a scenario was presented to help explain the researchers' results. In this scenario, Alice is a power systems operator and Bob is an adversary who hijacked the communication channel, allowing him to report inaccurate sensor measurements. Bob is using what's called a replay attack, and he presented old values from a day an outage occurred. Bob's intention here is to force Alice to shut down the system and remediate the issue, even though nothing is technically wrong with the power system. Bob is just spoofing these values. However, Alice starts the perturbation analysis system. The analysis tool then selects a random perturbation key. As shown previously, these keys were computed with MATLAB to produce accurate and fast linear predictions without adhering the function of the system. Bob's spoofed measurements will not have been changed to reflect the new system state after the perturbation analysis was initiated. Therefore, Alice noticed that the observed values she is seeing from the sensor measurements are incorrect. She is able to validate her assumption by comparing the expected values and the observed values. Alice is able to get the expected values because it's a known perturbation and she already knew what the expected values were. The goal of the solution in this presentation is to detect malicious data injection. Unfortunately today, current solutions are lacking and are not equipped to detect an adversary from maliciously injecting data or spoofing measurements. The solution today is really just to detect faulty sensors and anything working incorrectly with the system. Therefore, using perturbation analysis, the operator is able to have a robust system to detect an adversary from spoofing measurements or injecting malicious data. By running a regular perturbation analysis, the operator is able to potentially inject his or her own perturbations into the system and measure the results of those values. Then the operator is able to run the same perturbation analysis on a live system and compare those two values. And if the observed and the predicted values are outside a certain bounds, the operator is able to determine that maybe an adversary has infiltrated the power system or any other control system. The really great part about this solution is that it's very unpredictable. An adversary would have a very difficult time to discovering what perturbation the operator is injecting into the system. In this case, the adversary would need to know the system topology, and he or she would need to know the perturbation the operator is running on the system. And the adversary would actually need to adjust those values to match what the perpetrated values should be. And even though knowing the perturbation analysis is also very difficult for the adversary to find, there's also a defined key space placed into the solution. The key in the key space could be a vector of line impedance changes, and each key is under a certain constraint that's determined by the operators or designers. Like I mentioned before, the example in this paper was the designers wanted the key not to cause the system to lose more than 1% power loss. Essentially, creating a cybersecurity solution that breaks the system's functionality is not good for the system, or there's really no point to it. And malicious data injection is not only a problem in power systems, but also machine learning algorithms. So even though this solution focuses very on control systems and industrial control systems, this concept can be able to move over to potentially fix machine learning algorithms and other data-focused products.